maybe it's hard. I'm not sure.
I think
It's a beautiful book.
What's the title of it?
It's called Geometric Methods in Classical Mechanics, or no, Mathematical Methods in Classical Mechanics. But it doesn't assume you know what a manifold is or anything. Configuration space.
this is what I had in mind, but then when I realized that we need first to learn some photos, then saying no.
You're live, by the way.
Okay.
Yeah,
So,
I'm gonna, yeah,
Check those.
you guys can just stop working, don't worry about it, money now.
Not worry about it either way.
See a little bit.
Yeah. Yeah, I can. So I think common and I think this is yeah, I think that I was hoping for a what is it? If it looks loud, then I might get something. Because with books now, so in the past, I had the problem that I couldn't sound from my computer. Now I have the opposite problem. Yeah. Something for books. No, I don't know.
All right, so, so I should recall from last time, what it means for a surface length to be in normal form. Back to the height function. And the three conditions are that h of every cap is 2, h of every band is 0, and h of every cup is -2. And of course, these numbers are sort of chosen at random. And the theorem of Kawauchi, Shibuya, and Suzuki, 1982, is that every surface length in normal form, meaning it can be isotope until it satisfies these conditions. So I think the first thing I want to do today is just to sketch a rough sketch of the proof of this. So the first step is similar to what we did when we were trying to put a link in bridge position, namely for every local maximum or local minimum, we find an arc emanating either up or down from it. We use that arc to raise the minimum up and down. So, so we can use a gradient flow line emanating from a local max to raise all maxima above all critical points, all other critical points. And such that they have the same height. Okay. And then similarly for the minimum. Okay, so, and then the second step, which is something I mentioned earlier, is that in an epsilon neighborhood, the upshot of these two steps is that essentially what we see is at some height that's up top, we have a bunch of these flat caps. And then in between, we have these sort of bandy pieces. Look something like this. These little level bands. More arrange that. We have our cups. Okay. So let's let, we'll denote the caps by C plus, and we'll denote the cups by C minus, and we'll let L minus be the boundary of the cups, and L plus equal the boundary of the caps. So that's these unlinks that we see in these top and bottom levels. And then denote these bands by B sub I. Maybe that's B sub I minus 1. And we'll make the, the convention that the ith band occurs at time t I. And then we can, since we can always rescale, we can always reparameterize our target space, so that now we have the caps where we want them to be, and the cups where they want them to be, and all of these bands in between. Okay, nothing too crazy so far. So step 3 is to consider the interval. So what we're going to try to do now is we're going to try to straighten the surface out from bottom to top. Okay. So we want to consider the interval -2 to T1 first. Okay, so this is the interval between the cups and the first band. Okay. And then the claim is that by an isotopy of S that is supported, it's supported on the interval, on the portion of the force sphere given by -2 to T1 plus epsilon. Okay, so it's essentially supported between the level of the cups and a little bit above the level of the first band. It's supported there, and that is the identity on this bottom level, the height -2 slice. Sorry, 3 things in this list. By an isotopy of S that is supported on the force sphere, that is the identity on this level set, and that preserves level sets. These level sets T for T in this interval, T1 plus epsilon. So by an isotopy of this sort, oh, I think I changed my mind about what I want to call these things. What did I end up calling? I think I ended up calling D. Okay, let's change the notation for the concentration. This is not super important, obviously. we'll call them D plus and D minus, since they're collections of disks or conventions later. So we can arrange this portion of our two knot, or sorry, our surface knot. So the portion from -2 to T1 has a very nice form. What we see is and then we see our link L minus times -2 to T1, and then we see our band B1. So in other words, what we arranged is that we essentially have all these cups, and then emanating from each of them, a vertical cylinder sitting above each cup to some specified height here, and then at that top height we also see if I can do this right. Should I make this a little better? So we have these cups and cylinder, and then at the top here we have a band. And I guess the only thing to sort of remember is that this link L minus could be sort of a complicated. I've drawn it very standard, but it could be a little more complicated, or alternatively, this band could be a little bit complicated. But this is the picture for this portion of the surface. So it's the cups, then the boundary of the cups flung vertically upward through this interval, and then the band attached there. Okay, so we've by using this isotopy, it's sort of like combing out any wrinkles or wiggles in the surface. You sort of push them up until it's straight on this interval. So that makes sense. Okay, and so we're going to repeat this on each interval. I guess T sub I, so T sub I plus 1, and then also on T sub N to 2, I guess, where N is the number of bands. Okay, so we're going to repeat on this by a similar isotopy. So the isotopy will be the identity at the bottom of the interval, and it will preserve level sets, and it will straighten out everything above it. So we can arrange. We arrange that the surface on this interval looks like the I band. I need to set up some notation here, guys. Oh, yeah. And then the I plus first band, where L sub I is the result of resolving the link L sub I minus 1 along the band B sub I. Get the index right. L plus equals Ln. L0 equals L minus. Now let me just stare at this, right? I guess that seems right. I think it's wrong in my notes. What do you think? Is it right? Does it seem right? This is either I or I minus 1. I think it's right. Okay, so this is step 4. Lots of step 4s. And then so, okay, good. So we've arranged that we basically have this like vertical surface knot where every once in a while we just basically have cylinders, and then every once in a while we see a band which basically looks like this. We have 2 vertical faces coming up, and they switch. There's this flat top, and then they grow on the other side. all the way up to the caps.
I have a question.
Yeah, please.
Based on what I remember for your conventions, might be wrong, but I thought that that picture really wouldn't be more complicated than that, at least for the first one.
That's almost right. So one thing I didn't say that I could have is that we could have, I mean, if the boundary of the cups, oh, I see what you're saying. But this band could be, it's flat, but it could be a complicated band in this link. Okay. That's right. You're right. The cups are sort of the simplest possible disks. That's good. And these cylinders would be like really skinny. And then as soon as you attach a band, almost certainly that band is going to do something interesting. And then this thing will be like very skinny. Okay. It's a normal form. Well, the fact that H doesn't have any critical points. So when we, like this notation basically means flow the link up. The Morse function either on S4 or on a different manifold, then we would encounter weird critical points in this flow that we would need to be very careful about. Yeah, I mean, it's possible to define something of a normal form for a surface not in a Kirby diagram. Cool. Okay. So the last step is, now let's assume by reparameterizing that T1 is 0, the height T1 is 0, so that first band lies at height 0, and we can into this level set S4 0. And we do this for I equals, I guess, 2 up to n. So now that we've arranged this thing to have a nice product structure, we can sort of start pushing things down. So let's look at what happens if we try to do this. We'll just draw a schematic. All right, bear with me here for a second. This goes down. Yeah? Okay. So this is the band B sub I, let's say I minus 1. And so this is sort of a schematic because we're seeing these different levels. This is supposed to be what I was talking about earlier. And then up at this top level here, we see the next higher band. So there's a couple of possibilities for sort of where this band could live. Right, so it could sort of live there. It could live there, say. In terms of endpoints, that's kind of the only case. And so you see what we want to do is we want to just flow it down until it lies in this level. Okay. At which point, sort of, there's 3 possibilities. So once that red band, or once the orange band lies in the same level as the red band, a couple of things can go wrong. I mean, we'll just do them here. So there's 3 cases. So the first case is, as always, I perfectly managed to switch the colors in my notes without failing. Okay, so the first case is that it's sort of this first one I've drawn where the endpoints of the bands project down onto this link Li something. And the endpoints of the band are disjoint from this band. And parts are disjoint from the band. So as sort of bands in S3, they're just straight up joint. Successfully push the band case. And there's two bad cases. So the first bad case is that when we project this thing down, the endpoint of the band might just lie. See, that's like this case, right? If I push this down, then the endpoint of this band will lie on the portion of this link that corresponds to sort of like the new edge of this band when we do the resolution versus the old end where the band is attached. This mesh between, these links, this link and this link, and the orange one is attached along this link, right? Like that. And so it's possible that these coincide, and we need to fix this. And so what we do is we just sort of slide it off to one side or the other. And we do that, and we do that. We do one or the other. Okay, and that's just an isotopy up here in this level set. Okay, so that's and I guess you sort of collar it or something. Okay, and the next thing that can happen is we might have something like this, where the interior, or the sort of away from the boundaries of the bands, or away from the endpoints of the bands, the feet of the bands, they intersect each other. And in this case, so this I use the word slide, as we'll formalize later. And in this case, the verb is swim. And we can swim it to be on one side or the other. There's a choice. Did I get this time to me? No, I don't. Yeah, that when you sort of push this out, it will come over. And so so once we've done this, then we sort of repeat for each band, and then there'll be other bands that can intersect. But as we're pushing it down, we sort of just move it from side. And so we've arranged that all of the bands are lying in the zero height cross section. And so there's a scolium. You'll know what scolium is. Scolium is a corollary to something in the proof. To the result. Scolium is a corollary to something in the proof, but maybe not a statement. So the scolium is that the order, I should say the height of the bands can be permuted. The heights of the bands can be permuted freely, say between, in between the caps and the cups. We can move bands up and down however we please. That doesn't follow from something being in normal form, but it does follow from this, but we can straighten everything out. Because we push this band in to the surface, into the zero level set, we could push it bend out the other side. And same thing for any of them. Once they're all in, a better way to say this, once they're all in the zero slide, we can kind of push it up. Maybe it is a corollary. But if it's a corollary, then you can say it. All right. Okay. Yeah, so maybe I'll write this as an exercise. We can push the bands around so that, I'll combine this with this proposition. Or I'll say this. We can push the bands around so that S0 is a knot. I guess this is whenever S is connected. Okay, so this is something for you to think about. As you change the order of the bands, you can change what these cross-sectional links look like. Provided the surface is connected, you can arrange that the middle cross-section be connected by putting some of the bands above it. Some of them. If S is a 2 knot, meaning knotted sphere, with N caps and M caps, and S, I guess this is still inside the exercise, I think. This can be isotope, so that 1, as we saw above, S sub 0 equals K is a knot. 2, the surface from -2 to 0 is a disk with no maxima, and I guess maybe that's all I need to say. But the other thing you could say is that it has n-1 bands. And then 3, the top half of the surface, from 0 to 2, is a disk with no minima and n-1. All right, so that's just a little exercise for you to play around with, which will become a little bit more clear.
Are N and M switched?
I don't know. N cup. Well, my cups. Oh, sorry. I looked at the word caps and it looked like cups to me. So I checked to see if I switched them, and I looked here and I said, "Oh, it says cups." That's right. My handwriting is bad. Yeah. Also earlier, N was the number of bands, so it's all messed up. Okay, all right. So what I want to do now is I want to play around with an example of basically what I just assigned you as an exercise. So your exercise will be a lot easier after this. Okay, so consider the surface knot S in normal form with S, so what should S of 0 look like? So S of 0 is going to be given in the form. All right, time to draw. So this is what we were calling L minus. And then we have, oh, I can get my colors right here. This is going to be second band. These are going to be first band. So I claim that this is a surface not in normal form. So what do you need to check? To check that I'm not lying. Yeah, so what would need to happen if this, so, okay, maybe I'm not getting quite clear enough, but, or maybe I just didn't give you a long enough answer. But the idea is we put it in normal form, so we have the cups, then at the 0 level, all the bands appear, so that's what's shown. And then after that, we should have caps. So what two things should we check? Yeah, exactly. So the first thing we should check is that L minus is an unlink. And what's the second thing we should check? What happens if we resolve? I'll just X over here. Oh, so by the way, what kind of surface is it? What's the homeomorphism type of this thing? Oh, I guess you need to check what L plus is.
No.
Okay.
I mean, doesn't knowing the number of components of that link tell you?
Well, it tells you how many stands there are, but a priori you don't know how many caps there are.
Doesn't have to change that.
Both fission or yeah. For example, if I added a half twist to one of them, it's possible that adding a half twist to one of them would change the number of components in L plus. I think that happens
By the way,
to either of them. If you add a half twist to either of them.
resolving L minus along B1 and B2 is the same as resolving that link that you drew along B2. Because L minus is resolving.
No, L minus is this white link shown.
Oh, I see.
And L plus would be the result of resolving both those bands. Okay. All right. So anyway, let's the size of L plus is 2. So if you use 2 cups and 2 bands, then I think we saw last time that this is what a sphere looks like. Anyway, you can check if this is a sphere. All right, let me finish drawing the schematics. She distracted me from. Never know where you're going to go. So here's what I want to do. I want to push B2 and B1 lower. Okay. So I guess one way, I don't know what the best way to think about this. Maybe we still want this to, yeah, so okay. Maybe I want to push B1 down to height -1, and I want to push B2 up to height +1. And I want to see how my 0 level changes. And so what does that look like in this picture? Well, that means we do our cups, and then we resolve B1 first. We resolve B1 first. And so let's see what that gives us. Okay, you can see, apologies. And then we can just think of B2 as sort of still living in there. As you can see, what we get is we get an interesting knot, and this is actually the knot. I haven't told you what pretzel knots are yet, but you can kind of guess from the notation of the picture. This is the pretzel knot 3 minus 3, 3. Okay, fine. So now let's do the opposite, which is now let's resolve B2. I should have added the adverb first. I want to resolve B1 first. Going up, I would still resolve B2, and sort of if I wanted to go back down, where's my dual? My dual is sort of down here. If I wanted to go back down, I would sort of resolve this band here. So the next schematic I'm going to draw, sorry, I have to draw this again. So now I want to do it in the opposite order. And just keep in mind that these descriptions are just related by ambient isotope of our knotted surface. So all of these are the same knotted surface. So now we resolve the second band first, and let's see what we get. Here's this. And we still have B1 hanging around, and we can remember sort of where B2 would be. This would be the dual band to B2. Okay. All right, so, well, what is that guy? It's the unknown, that's right. This is just the unknown. And in fact, we can even sort of, we can consider the portion of the surface S0 to 2. We can consider the top half of this surface in a little bit more detail. So this is the half of S, above the equator, when I guess beta 2 was resolved at height -1. Okay. And so let's just see what happens if we consider this thing. Well, since we're only considering the top half, we can forget about beta 2. That happened in the past. And so what we see is that this thing really unwinds quite a bit. Does something like this. Okay, and if we carry on, what we end up seeing is just something like this. So the half of S going up is it's this really simple disk. It's exactly what's shown in this schematic, right? So I should say that in this schematic, we have this pretzel knot here in the equator, and this schematic, we have the unknot here in this equator. What we see is a very simple disk going up. We just attach this sort of trivial band, and we get, if you resolve this band, this would give just some simple caps. So what we see is that there's actually this disk here. There's this disk here, which sort of cancels this band. We'll make this precise soon, but I guess you can think of it as this disk here. And the idea is that this disk, because this band is trivial, can be pushed down to lie in the same level as the band and can be canceled. Okay. And you can even see this disk in this picture, I think. And then it bubbles up over that. And so what I'm doing here, you can think of this isotope that I did as being undone going up to here, and then pushing this back down, sort of pushing this disk down, back down through the isotope until it lies in this picture right here. So the upshot is that a cap can be canceled with band number, what this blue one? Band number 1 in this viewpoint, the second viewpoint. And you might not be surprised to learn that the same thing can be done in the bottom half of this description. So I consider the sort of disk from 0 to +2. You could also consider the disk from 2 to -2. And you can also cancel, similarly, the 2 can be canceled with a minimum of S. Okay. And these cancellations are ambient isotopies. So this implies that S is isotopic so that it has no bands. Okay. And therefore, S is the unknotted two-spin. Okay. Mm-hmm. There's even a way to isotope this with its bands. This is actually able to draw, but I won't go through the details. Detour. Okay. So just to answer Jason's question, actually, we saw this ribbon right away because attaching the blue band, that's the ribbon disk, the sort of, I explored orange band. The theorem about normal form was that all the bands can be put in the same level. But now you can have lots of sort of normal forms. You could have all the bands at different levels if you wanted. I think probably from now on, normal form will just mean the bands. From now on, normal form will just mean the bands are in between the maxes. Because these are
Which is a present mode. Very what we are saying.
yeah, so now, I mean, well, actually, I'll keep beta 1 here. Or P1 here, even though it's B1 dual. We need to remember it's going down. But what you can see is it's actually symmetric with the orange one. So the fact that really believe me that if I resolve this band, I get nothing because it's just this picture. Well, resolving this one has the same effect. 1962, when he was really doing things not exactly the same. And action, which cross section or this in terms of show up as cross sections of knotted or unknotted spheres. And for definition, a knotted is slice if is S intersect for some 2 not S. S to the next 4, and is doubly sliced if K is the unknotted two-sphere intersect the equator of S squared.